Lighthouse Scientific Education presents a lecture in the Atomic Structure series. The topic, Valence Electrons, Octet Rule, and dot structure. Material in this lecture builds upon the previous lectures, quantum mechanics, and electronic configurations. This lecture looks at three useful tools that follow the electronic configuration of the atom. Valence electrons. We will determine them directly from electronic configuration and from the periodic table. We will use valence electrons as the basis of the Octet Rule and in developing electron or Lewis dot diagrams. We start by revisiting the stratified energy level diagram to state that electrons in the uppermost occupied energy levels of the atom are the ones that participate in chemical reactions. In this lecture, we are taking the lessons we learned in determining electronic configurations to prepare ourselves to transition from discussing the atom to considering how atoms form compounds and molecules, real chemistry. For the atom represented by this diagram, the electrons in the 3s and 3p orbitals are the ones in the uppermost occupied energy levels. But why just concern ourselves with these orbitals? Well, the uppermost orbitals have the highest energy electrons. Also, these electrons are the furthest away from the nucleus and are therefore the least tightly held. The combination of being of a higher energy and held with a looser grip make the upper orbital electrons natural candidates for the sharing, borrowing, and releasing of electrons that define chemical reactions. And those electrons located under the upper orbitals? If we look at the electronic configuration of just those electrons, we see that they have the same electronic configuration as their nearest noble gas, neon in this case. And as we know, that configuration is particularly stable. Let's take a closer look at this. Once an energy level is completely filled, those electrons do not participate in chemical reactions. There are quotes around do not because things in reality are always a little more complicated than they first seem. However, we will stay with the do not in this lecture. So, where are the energy levels, as designated by the principal quantum number n, complete? That's right, it is at the noble gases. N equals 1 is complete at helium. N equal 1 only has an s orbital, and 1s2 is that orbital filled. A filled energy level can use the bracket shorthand. Brackets helium is equal to 1s2. For n equals 2, the energy level has 2s and 2p orbitals. The noble gas neon has the right number of electrons to fill those orbitals, brackets Ne. If we replace 1s2 with brackets helium, we can more clearly see that the outer occupied orbitals are 2s and 2p. The same argument can be made with argon. The 3s and 3p orbitals are the outer occupied orbitals. They come after the filled N equals 2 energy level of neon. When the energy level is 3 or higher, there is a complicating matter. These higher energy levels have additional orbital types like D and F that require additional consideration. But for now, we'll just focus on electrons in the s and p orbitals. Electrons in the s and p orbitals, after the last noble gas configuration, are called the valence electrons, VE for short. Valence electrons are a very important concept in considering chemical reactions and molecular structure. It is worth our time to make sure that we are confident of which electrons in an atom are characterized as valence electrons. Presented here is a list of the first 18 elements along with their electronic configurations. We're going to note the valence electrons for each element. Revisiting the definition, electrons in the s and p orbitals after the last noble gas configuration are called valence electrons. To be clear, we will highlight the noble gas configurations. Helium is the first noble gas, and both of its electrons are called valence electrons, even though they are technically not after a noble gas. Then there is neon. It has a total of 8 2s and 2p electrons, which come after the noble gas configuration of helium. Then finally, there is argon. It has a total of 8 3s and 3p electrons, which come after the noble gas configuration neon. The pattern 2, 8, 8 is an important arrangement for these first 18 elements. It is a recognition that it takes 2 elements before the n equals 1 level is filled, and 8 more elements to fill the s and p orbitals of the n equals 2 level, and an additional 8 more elements before the s and p orbitals are filled in the n equals 3 energy level. We will see this pattern 2, 8, 8 again and again. For instance, if we look at the periodic table, it shows us that there are 2 elements in the first row. Helium has been moved to its other position, the one next to hydrogen, for this demonstration. There are 8 elements in the second row and 8 in the third row. Okay, now to listing out valence electrons for each element. For elements in the 1s block, hydrogen's lone electron will be considered a valence electron. Helium, as mentioned, has 2, and that caps the valence electrons in the n equals 1 level. We will no longer be considering electrons from the 1s orbital. It's full. For the 2s block, lithium has 1 electron after the noble gas configuration of helium. Beryllium has 2 electrons after the noble gas configuration of helium. Now, including the 2p orbital block, boron has 3 electrons after the noble gas configuration of helium. 2 are from the 2s block, 1 from the 2p. Carbon has 4, 2 from the 2s and 2 from the 2p. Nitrogen has 5, 2 from the 2s block and 3 from the 2p. Oxygen has 6, 2 from the 2s block, 4 from the 2p. Fluorine has 7, 2 from the 2s block and 5 from the 2p. And as we stated, neon has 8, 2 from the 2s block and 6 from the 2p. We will no longer be considering electrons from the 2s and 2p orbitals because they are full. For the 3s orbital block, sodium has 1 valence electron after the noble gas configuration of neon, 3s1. Magnesium has 2 valence electrons, now including the 3p block. Aluminum has 3 valence electrons, 2 from the 3s block and 1 from the 3p. Silicon has 4, phosphorus has 5, sulfur has 6, chlorine has 7, and argon with the stable 8 arrangement, 2 from the 3s and 6 from the 3p. Viewing just the part of the electronic configuration with valence electrons, we see that as we go up by 1 in atomic number, we go up by 1 in valence electrons until we reach a noble gas. Then there's a reset to 1 and the incremental increase begins again. There is another and probably easier way to obtain the correct number of valence electrons, and that is to use the periodic table of elements. Look at your periodic table. Notice that at the top of each column in the S and P block, there is a Roman numeral followed by the letter A. The A stands for main group elements. The Roman numeral tells us how many valence electrons the elements in those columns possess. Now, some tables don't use the Roman numeral system. They just number the columns from 1 to 18. We will relate the two styles as we go along. Look at the first column on the left. It has a Roman numeral I, or 1. Those elements have 1 valence electron. On top of the second column, there is a 2. These elements have 2 valence electrons. Hopping over to the P block, there is 3, 4, 5 as a V, 6, 7, and 8. Each is a count of the valence electrons in that column. Again, helium has been moved over to its other position, the one next to hydrogen for this demonstration, since it has 2 valence electrons. The Roman numeral style and the regular number style at the top of the columns are the same for the first 2 columns. But when we go to the start of the P block, the Roman numerals continue on at 3, but the regular numbers jump 10 values to 13. Reasonable, considering that they are counting the 10 columns of the transition metals. It's easy to reconcile the two systems by subtracting 10 from the regular number style. That is, 13 represents Roman numeral 3 and its 3 valence electrons, 14 represents 4, 15, 5, and so on to 18, representing Roman numeral 8 and its 8 valence electrons. To restate the use of the periodic table in finding valence electrons, the elements in the first column have 1 valence electron. Moving across the table, the elements in this column have 2 valence electrons. These have 3, 4, 5, 6, 7, and the noble gases have 8 valence electrons. Using the periodic table is an easier way to find the number of valence electrons, but being able to get them using an electronic configuration shows a deeper understanding of what valence electrons really are. It's best to beware of both procedures. A little quiz should see to that. Given carbon's electronic configuration, how many valence electrons does it have? We see that after the filled 1s orbital, it has 2 electrons in its 2s block and 2 in its 2p. That's 4 valence electrons. Consulting the periodic table and finding carbon, we note that the Roman numeral on the top of the column also gives us 4, as does subtracting 10 from 14. What about fluorine? Consulting its electronic configuration, we see that it has 2 electrons in the 2s orbital and 5 in the 2p block, for a total of 7 valence electrons. Using the periodic table yields the same value of 7. One more, silicon. Looking at the electrons that come after the last noble gas configuration, we find that it has 2 electrons in the 3s orbital and 2 in the 3p block of orbitals, summing to 4 valence electrons. Not surprising, the value from the periodic table also provides us with 4. Even though carbon and silicon are in different rows, they have the same number of valence electrons. The reason we spent so much time and effort in determining the number of valence electrons is that we're going to need that number. The first place we will apply it is with the Octet Rule. And that rule says that atoms with 8 electrons in their outer shell, and we're only talking s and p orbitals, are the most stable. The 8 comes from filling the s orbital, 2 electrons, and the 3 p orbitals, each holding 2 electrons for a total of 6. 2 plus 6. Noble gases have an octet, S2, P6. One can also see that they fall under the heading of 8A. The octet rule mostly applies with elements in the second and third row. A duet or 2 rule can be used for row 1. Helium is a noble gas with 2 electrons. And as a heads up for chemistry to come, atoms interact with other atoms such that each has 8 valence electrons, like their nearest noble gas. There are some limitations to this statement, but it holds for a lot of chemistry covered at this level. It's worth sketching out a model of the atom consistent with the octet and duet rules. Using a simplified description of the atom and orbital shells, we can generate a visual model of the atom that can help us better understand chemistry topics like atom-atom interaction, ion formation, and conveniently will lead us to our next topic, Lewis diagrams. Let's see how this model works. We begin by drawing the positively charged nucleus as a small sphere. Starting with the duet rule and the n=1 shell, we can represent that first shell as a circular sphere around the nucleus. Duet means 2. Our first shell is complete with 2 electrons, paired electrons. 2 dots are added to the first shell as a representation of the paired electrons. Next we move to row 2 and 3, which follow the octet rule. Row 2, with its 8 elements, gets a shell that can hold up to 8 electrons. Borrowing Hund's rule, which has opposite spin electrons pairing, we add pairs of dots to the second shell, and we add them as far away from each other as possible. Not a bad idea, since negatively charged electrons repel each other. Therefore, there are 4 sets of dots. For row 3 and its 8 elements, we add a new larger shell, which can also hold 8 electrons. As with the second shell, these electrons are paired, and the pairs are placed as far apart from each other as possible. This is our octet version of the atom, or at least atoms having 18 or less electrons. Still, it is only a model, and it is best used as a bookkeeper that keeps track of valence electrons. Speaking of 18 electrons, the pattern of electrons in this atom with full shells is that same 288. That pattern comes up regularly in the study of chemistry because it represents the maximum number of valence electrons in each shell. 2 in the first, 8 in the second and third. It also helps us explain the formation of ions, and it leads us to our next topic, the electron dot diagram, or Lewis structure. This is a useful way to visualize the valence electrons around an element, or an atom. It is very similar to the model of the atom we just constructed with the octet rule, but it is only concerned with the last, or the outer shell, electrons. Let's begin with an overview. The symbol for the element is written in the center. 1 dot is added in a specific pattern for each valence electron. Along with the octet rule and the duet rule, the electron dot diagram can be useful to help us understand how atoms form molecules and ions. But that's a lecture for another time. First, we need to be able to construct diagrams for just atoms. Determining the Lewis dot diagram of an atom is similar to that of filling its electronic configuration. It's not as accurate as an electronic configuration. Like the atom model, using the octet rule, dot diagrams are practical tools. We're going to construct a platform for generating dot diagrams. We will use a capital E as a generic stand-in for all symbols of elements. We will use dots to represent valence electrons, and we will give this element E 6 valence electrons for demonstration purposes. The dot diagram, or dot structure, can be considered as using 4 equal energy orbitals. Loosely, we can view this as putting the single s orbital of an energy level on the same footing as the 3 p orbitals, giving us 4 equal energy orbitals. And as we did with the model of the octet rule, place these 4 orbitals, pictured as boxes, around the symbol of the element and put them as far away from each other as possible. Our next consideration is how to add electrons to the boxes. For that, we will consult the Hund rule and the Aufbau principle. The Hund rule limits these orbitals or boxes to no more than 2 electrons. We can generate the Hund rule on this diagram by dividing each box in half. There are 8 half boxes. The format of the dot diagram is complete. Now the pattern of adding electrons is dots. According to the Aufbau principle, electrons are added to equal energy orbitals before pairing. Remember how, when we were deriving electronic configurations, we added 1 electron to the 2px, then another to the 2py, and then another to the 2pz before any pairing occurred? Same thing applies here. One electron is added to each of the equal energy orbitals before any pairing. That uses up 4 of element E's 6 valence electrons. It is only after each box has a dot that we continue assigning dots by pairing. The additional 2 valence electrons are paired. A couple small details to clean up. We do not actually have to include the boxes around the element. They were used here to develop the concept. Also, since the boxes represent equal energy orbitals, it is not strictly incorrect to start with a dot in a box other than the one on top. It is, however, by convention that we start at the top box and go in a clockwise manner around the symbol. And that is the basis of the dot diagram. We will use some basic rules for constructing Lewis dot diagrams until we feel comfortable with the procedure. Begin by writing the symbol for the element, and yes, it will be placed at the center. Determine the number of valence electrons for the element. This can be found by using the electronic configuration or the Roman numeral or column numbers above the column on the periodic table where the element resides. Now add electrons as dots to each box, and that's an orbital, around the element symbol up to 4 valence electrons, and do this in a clockwise fashion. If there are more than 4 electrons, repeat the pattern of addition to each box and pair. Shall we give it a try? We start by writing the symbol of the element. Carbon has offered to go first. Find the number of valence electrons for carbon. Referring to its electronic configuration, we see that the electrons coming after the last noble gas are 2s2 and 2p2. 2 plus 2 equals 4. Carbon has 4 valence electrons. The dot diagram will have 4 dots. The next step is to add dots up to 4 around the element in a clockwise manner. 1, 2, 3, 4. Note, we have added 1 dot to each of our box without pairing, and that uses up all our valence electrons. This is carbon's dot diagram. So the last step about pairing electrons isn't required here. We should do another one, step by step. How about fluorine? We start by writing the element symbol F. We need to find the number of valence electrons for fluorine. According to its electronic configuration, there are 2 valence electrons in the 2s and 5 in the 2p. That's 7. We could have also located fluorine on the periodic table and note that the Roman numeral VII, or 7, on the top of the column. Column number 17 minus 10 would also yield 7. Fluorine has 7 valence electrons. The dot diagram will have 7 dots. Now we add the electrons as dots around the F one at a time, starting at the top until we get to 4. 1, 2, 3, 4. That's 4 of 7. We still have 3 more dots. Step 4 has us repeating the pattern of adding dots one at a time. These dots, however, will pair, starting at the top, 5, 6, 7. 3 boxes are filled, and 1 is half filled. All right, now we're going to run through the first 18 elements and generate dot diagrams for each. We are attempting to develop the pattern of using the rules so that we don't have to rely on using the rules. To speed up matters, we will use a table that states the number of valence electrons for each element. It's okay to use a table. Starting with hydrogen, and its 1 valence electron. Its 1 dot goes in the top box. Helium, 2 valence electrons. 1 on top, 2 on top. Looks like the noble gas helium is going to follow the duet rule. It will not have 4 boxes around the element symbol. It will have 1 box or orbital on top, and the dots will pair. Okay, we're just going to have to remember that. On to lithium with its 1 valence electron. Remember, valence electrons come after the last noble gas configuration, and that is helium's 1s2. We will put the dot on top, and we see that lithium and hydrogen have the same dot diagram. Makes sense since they are both under the 1a heading. To beryllium, it has 2 valence electrons, one on the top, the second added in a clockwise fashion. Boron, 3 valence electrons, 1, 2, 3. Carbon, it has 4 valence electrons, 1, 2, 3, 4. All are added in a clockwise fashion, and each of the boxes has 1 dot. Any more and we will have to pair, which is the case with the 5 valence electrons of nitrogen. The first 4 go in a clockwise fashion, and the 5th pairs in the top box. Dots added after the first 4 dots repeat the pattern of going around in a clockwise fashion, and that includes starting at the top. Oxygen has 6 valence electrons, 1, 2, 3, 4, and pairing 5 and 6. Fluorine's 7 valence electron dot diagram will look like oxygen, but with 1 more dot. 1, 2, 3, 4, pairing 5, 6, and 7. Neon, the noble gas, has a full octet. That means 8 valence electrons and 8 dots. 4 dots around and 4 more in pairing. There is no more room for dots, that is electrons, on this element, and that is why full octet atoms are so stable. It also means that as we move to the next element, we will be starting a new shell and starting back at 1 valence electrons. Row 3 of the periodic table starts with sodium. We are at the beginning of a new set of valence electrons coming after neon. Sodium has 1, and it goes on top, like hydrogen and lithium. Each is a member of the column 1a. Magnesium has 2 valence electrons, 1, 2. But so does beryllium. They both reside in column 2a. Aluminum, with its 3 valence electrons, shares the same dot structure as boron, as well as sharing a column on the table, 3a. Silicon has 4 valence electrons, as does carbon, 1, 2, 3, 4. They are found in column 4. Phosphorus and nitrogen both have 5 electrons, 1, 2, 3, 4, and pair the 5th electron. They share the same dot diagram and have similar physical properties. You can find them in column 5. Sulfur and oxygen both have 6 valence electrons. Sulfur's dot diagram is going to look like oxygen. 1, 2, 3, 4, pair the 5th and 6th valence electron. They share the same dot diagram and have the same physical properties. They belong to column 6. Is the value of the dot structure becoming clearer? The halogen chlorine and fluorine are both 1 electron short of a full octet. It shouldn't be too surprising to find that these atom types readily steal an electron to fill their octet. The 7 dots around chlorine have the same pattern as the 7 dots around fluorine. They do, after all, reside in column 7. And finally, the noble gas argon. It does have a full octet and is a stable atom type, just like the other noble gas, neon. Try your own pass through the first 18 elements and this important topic will quickly become more comfortable and add as a skill set. Let's recap what we've learned. Electrons in the uppermost energy levels of the atom are the ones that participate in chemical reactions. The ones beneath them are in stable noble gas electronic configurations. Electrons in the s and p orbital after the last noble gas configuration are called the valence electrons, VE. We use valence electrons in the Octet Rule. Atoms with 8 electrons in their outer shell, specifically s and p orbitals, are most stable. The 8 comes from filling the 1s orbital, 2 electrons, and the 3 p orbitals, 6 electrons. A duet or 2 rule can be used for row 1. That means the first 3 rows go 2, 8, 8 for valence electrons. The electron or Lewis dot diagram or dot structure is a useful way to visualize the valence electrons around an element. The rules for creating a dot diagram begin with writing the symbol for the element. It will be in the center. Determine the number of valence electrons, either through the element's electronic configuration or the column in the periodic table. We can either use the Roman numerals or the column numbers above the element. Add electrons or dots up to 4 in a clockwise fashion, one at a time, to each side of the element symbol. We call these equal energy orbitals boxes in this lecture. If there are more than 4 valence electrons, repeat pattern of addition to each side and pair electrons or dots. And that concludes our lecture on valence electrons and their use in the octet rule and the dot diagram. This is a useful topic that makes sense with a little practice.